Second, I'd really like to thank the United Scientific Group for this opportunity to give this keynote presentation for its 2025 year physics conference. So let's start. I'm going to discuss some dark matter and gravitational details that explain otherwise seemingly unexplained cosmic data. The structure of the presentation is that of a technical paper. And by the way, there is a preprint available, and I'll repeat my email address and the preprint at the end of the talk. So this takes the structure of a technical paper, and let's start with the introduction. We will run all the way through conclusions and one appendix. Here are two 90-year-old major opportunities in the field of cosmology. In the 1920s, at the Mount Wilson Observatory near Caltech, people discovered that there was more than one galaxy in the universe. And this opened up the question as to what is the large-scale evolution of the universe. A modern diagram in the lower left suggests a current view as to what's going on. Time runs from the left to the right. And if you imagine two galaxy clusters, one of which traces the upper edge of that diagram, and the other of which traces the lower edge of the diagram, one would see that they're nearby and they're not colliding. They move apart very rapidly for a very short period of time, and then for a multi-billion-year era, they're still moving apart, but the rate of moving apart is slowing down. And then for the right half of the diagram, roughly, for the most recent multi-billion-year era, the moving apart is increasing and accelerating. So this is actually a long-term evolving mystery, and there is not a really good solution for that at the moment, other than maybe what I'm going to talk about. The other one starts in the early 1930s, same observatory, attributed to a different scientist, looking at galaxies and then by then known galaxy clusters. People determined that there seemed to be more gravity than they could account for based on the matter that they could see. And so the question for 90 years here has been to explain how that happens. And the term that was invented early on as a possible explanation was dark matter. I'm going to offer you a unified solution to both of these challenges and maybe a major step forward in terms of cosmology. The themes for my research are really very simple. Let's take inspiration from data, and let's reuse familiar physics as much as we possibly can. So here's a preview as to where we're going with all of this. For the dark matter area, we're going to suggest that if you take all the known elementary particles and throw out the photon, and then make a total of 6 copies, roughly the same copy, but not quite, we'll call them isomers, 6 isomers of that elementary particle set, that in fact, one of those isomers underlies what we see. That seems to be pretty obvious. We call that ordinary matter. And the other 5 isomers underlie the dark matter. And they will evolve differently so that 2 of the isomers have atoms and that sort of thing, and the other isomer evolves into essentially neutrons that can't decay, the other 4 isomers. On the large scale side, we're going to do something very simple, which is look at 2-body gravitational forces. And we're going to find out that as we add properties beyond mass, that we can have some forces that actually push things apart and might be able to account for the diagram that we talked about a moment ago. So here in more detail is a list of the phenomena that we want to explain. Elementary particles, including dark matter ones, dark matter stuff made from the elementary particles, a bunch of measured ratios of dark matter presence or effect to ordinary matter presence and effect. And I'll suggest that all of those explanations lead to quantitative results. Qualitatively will explain the eras and the rate of expansion of the universe. This this chart indicates that the idea of isomers pervades the whole thing, and the two-body gravitation idea is necessary for explaining some of the ideas. Now, in detail, here are some of the ratios, in fact, the ratios. For galaxies, many galaxies are measured today as having ratios of dark matter presence to ordinary matter presence of 5+1. Some galaxies about 4:1, some galaxies essentially all ordinary matter, some galaxies essentially all dark matter. So we're going to explain that. And then the other ratios for very large scale things, so-called densities of the universe, or gravitational effects within galaxy clusters, 5+1, and one sort of outlier, but very interesting and important, happened in the last few years. That's a measure of the depletion of cosmic microwave background radiation. That's that thing in the chart that's called afterglow light, from about 380,000 years after the supposed Big Bang. The depletion of that over billions of years, people estimated it theoretically, they measured it experimentally. It's attributed to interactions, hyperfine transition interactions with hydrogen atoms, and they got twice as much depletion as they expected. So now we'd be in the methods section of a scientific paper. And very quickly, to introduce this, the methods include giving a very detailed specification for dark matter. We're going to deploy a new type of multipole expansion, very simple mathematics, to look at the gravitational properties of objects, and we're going to find that some of them attract objects to each other and some of them repel objects away from each other. We need one idea to merge those two things together, which results in a very simple integer-based equation. And the solutions to that equation then give us the explanations for the phenomena. So let's start with the isomers idea. First of all, we've already pretty much talked our way through the idea that the ratios of 5+1, dark matter presence to ordinary matter presence on a large scale. And we've talked about that idea, and that just outright suggests that maybe there are 6 isomers and that one of them associates or underlies ordinary matter, 5 of them dark matter. If we factor the 6 into 2 times 3, then we're going to assert that the 2 associates with an idea of handedness. Elementary particle physicists say that all the known elementary particles, except the photon, of which we know, that do exhibit handedness, and this includes the leptons like the electron and all the quarks also, those particles are left-handed, and then what we assert is that there's a twin isomer that's just the same thing, but right-handed. And in fact, we have 3 right-handed isomers, 3 left-handed isomers. The factor of 3 is going to associate with something that's also pretty well known, and that is that the neutrino mass eigenstates, the 3 of them, do not match the neutrino flavor eigenstates. This is something called neutrino oscillations experimentally, and we're going to take advantage of that, generalize from that, and see that we get 3 different types of isomer pairs. So here we are, and for the isomer pair that we've talked about that includes ordinary matter and its right-handed twin, then that will be enough to explain this cosmic microwave background depletion. And we'll use the term it dovetails with the popular modeling notion of self-interacting dark matter. The other 4 dark matter isomers, as I indicated, decay or evolve into stuff that is basically stable neutrons that can't decay. These would be marginally electromagnetically interactive. And these four dark matter isomers would associate with the popular notion of collisionless dark matter. This is a chart that summarizes what we've just been talking about, gives numbers to the isomers and the isomer pairs. There's a column for handedness. The remarks I just made are sort of on the right-hand side of the chart. Let me spend a little bit of time on the middle columns there. Each of these columns is ordered by increasing mass. For the quarks, it's the geometric mean of the two quarks that go with each flavor. And so we always have, or each generation, we always have generation one, lowest mass. Those are the up and down quarks. And then it goes up from there. In the lepton area, lowest mass, is first. So the one there on the first line is an electron, the two is a muon, the three is a tau. And that holds for the twin pair. But in the other ones, the lowest mass isomer, lowest mass charged lepton has a higher flavor number. And it's due to that and the evolution of how things cool in the early part of the universe. Basically, for all six isomers, as things cool to the point where the three baryon or the three quark baryons make it into generation one, you have a preponderance of neutral particles as opposed to a preponderance of charged particles. But for the bottom four isomers, the flavor one lepton is too massive for the neutrons to decay, and so they just get frozen in as neutrons. So I think we've done that pretty well. So let's now go on and talk a little bit about two-body gravity, which was the second step in the methods. Historically, 17th century got the very familiar Newtonian gravitational force equation that involves two masses. In the 18th century, in electromagnetism, we have the Coulomb equation that involves two charges. In the 19th century, there was a flurry of activity around motors and magnetic fields and so forth. And by the end of the century, we have the Lorentz electromagnetic force equation, which we'll see later, Lorentz invariance, the underlying for special relativity, and electromagnetic properties beyond charge. We're going to take a relook at this sort of stuff later in the talk. And then a 21st century idea that I suggest that goes with the chart at the bottom, where we have a variety of properties of objects. We look at two objects, and in some cases we get gravitational push, as well as gravitational pull. To make this all work, we are going to use an idea of multipole expansions. This is very familiar mathematics and applied to physics. For example, people look at a smeared out distribution of mass, and then they do a multipole expansion, 1 over r term, 1 over r squared terms, 1 over r cubed terms, that approximate at a distance the potential that goes with that mass. We're going to do something similar in the sense that we're going to do 1 over r, 1 over r squared, et cetera, where r is the radius away from the middle of the stuff, expansions, but it's only going to be for one small object, and the terms in the expansion are going to be the properties of that one object. Mass would go with 1 over r. If we're in electromagnetism, charge goes with 1 over r. Magnetic moment goes with 1 over r squared. If we do this all out, and we'll do much more of this in the appendix, then for gravity, we get to the chart that you see here. Mass is a monopole, associates with a monopole potential, angular momentum internal to the object, dipole, moments of inertia, quadrupole, and so forth. The n sub 3s column refers to a number of threesomes. And if you look in the lower left corner of this chart, in order to do mass, you need to know where it is. That's one threesome. If you want to do angular momentum, you need mass plus an angular velocity, which is another threesome. If you want to do moments of inertia tensor, then you need position, you need three on-diagonal elements, you need three off-diagonal moments of inertia elements, and you get the N3S equals 3. Again, a preview of pull and push for interaction between this property of one object and the mass of another object. So that's what's going on here. Let's look at what we need to do to glue this together. We need an idea of instances of properties of objects. Why? Popular modeling suggests that all objects interact gravitationally with all other objects. So we're going to say that across the 6 isomers, there's one instance of the property of mass, and that one instance has a reach in terms of interactions of 6 isomers. Now, that idea will not work for electromagnetism because we barely, if at all, see dark matter. So we're going to suggest that each isomer has its own instance of charge, and that each of those instances, in terms of interactions, has a reach of just one isomer. If we're going to follow this means that we need to figure out reaches and instances for all of our properties. They will follow the equation that's up there in the upper left. The number of instances for one property times the reach per instance is 6. I've shown here a few of the solutions, but we won't go through those now because they're all on the next chart. So this is what we would get for some properties, gravitational properties, some electromagnetic properties. We've already indicated the idea of one instance of mass and a reach of 6 isomers. For angular momentum, gravity, angular momentum, the idea is going to turn out that we have 3 instances, one per isomer pair, and each instance has a reach of 2 isomers. So it goes on from here, and then the bottom 4 items on here are electromagnetic ones. 2 of them don't fall on this categorization scheme. Black body temperature is the property through which we see stars, and the hyperfine state is the one that we've already talked about, and I suggest values there. This is all we need now to explain a lot of things, but we're going to do one more slide, one detour here. We're going to look at that evolution of the universe chart in the lower corner there, and ask how to explain what's going on, and we're going to do it in a much more general sense. We're going to imagine that at the left end of this, that at the beginning of the universe, things are very compact, but dark matter, ordinary matter, everything is spread spatially uniformly. And what the argument here suggests is that as you move to the right, then neighboring clumps of similar sized stuff transit as the universe, quote unquote, expands or things move apart, transit a sequence that includes octopole repulsion or push through monopole pull, gravitational pull. So small things go through this first solar system sized clumps made up of atoms and dust and so forth, go through this very quickly. More slowly, galaxies, more slowly, galaxy clusters, and indeed for interactions between neighboring non-colliding galaxy clusters, we suggest that that upturn over the last few billion years is that they haven't made it to monopole attraction at this point. They're still in the dipole repulsion era. So now we can actually explain everything. So this is the results section of a would-be paper. A reminder of where we come from and where we're going, and now how we get the explanations. For the cosmic microwave background depletion, we've already done it. The 1-to-1 ratio, half of the depletion is hyperfine interactions in ordinary matter atoms. Half of it is depletion through that one isomer of dark matter that forms hydrogen-like atoms. The other 4 isomers don't form significant amounts of hydrogen-like atoms, so we don't do anything there. The galaxy formation scenario is much more interesting, I think. What happens here depends on that clumping and moving across from octopole to monopole sort of thing. Early on in the universe, reach one, gravitational quadrupole pole, pulls together from solar system sized clumps galaxies, early galaxies that are essentially all ordinary matter or essentially all dark matter. When reach 2 dipole push takes over, it pushes away some loose stuff that associates with the one isomer that is featured in the galaxy, and it pushes away all the stuff that associates with the twin isomer, the paired isomer. So we still have galaxies that are essentially all ordinary matter and galaxies that are essentially all dark matter. Then reach 6 monopole pull takes over and pulls in the nearby stuff, and you can get 4-to-1 galaxies. This all would have happened very early on. Most of the galaxies that we see today are the results of monopole pull between galaxies, merging galaxies, they stick together, and we get the 5+1 galaxies. So this is a very simple but very testable sort of thing to look at. Now, in terms of galaxy clusters, the larger things and densities of the universe, we've already explained 5-to-1 in terms of numbers of isomers. What about the plus in the 5+1 ratios? Well, there are many possible explanations. I can offer one. Maybe early in the universe, when things were very hot, there were very active reach 6 components of the electromagnetic interaction. Those reach 6 things, given that 2 isomers formed material and the others did not, would transmit a lot more energy away from ordinary matter and its twin into the other 4 isomers than the first 2 receive back. And so you get an imbalance. And that might be the extra or part of the extra in the plus, or the plus in the 5+1. There are plenty of other ideas. Popular modeling suggests many candidates for dark matter, including some elementary particles like axions, and that could be any or all of the plus also. For the large-scale phenomena, we move away from quantitative to qualitative. We pull out that sequence that runs from hexadecipole pull to all the way down, and we do a possible history of the universe. Some people suggest the idea of a big crunch in which everything came together. I would suggest that if there was such a thing, gravitational hexadecipole pull might be responsible for that. We need a way to turn it around, and then we suggest that one might have a Pauli exclusion bounce based on the idea that there would be fermion elementary particles and fermion stuff at that point, and Pauli exclusion bounce would occur. After that, we have the possibility of an inflationary epoch, and that would be driven by gravitational octopole push. And from now on, we're just going to talk about things between neighboring galaxy clusters. Now, there is, as far as I know, no direct data for everything we've just been talking about on this chart. The direct data kicks in for the earlier multi-billion year era, which I suggest for the decreasing rate of expansion. We have an explanation of gravitational quadrupole pull, at least at the beginning of that era. And then we have the later and possibly still current multi-billion year era of increasing rate of expansion. That would be the push that goes with dipole interactions. And then possibly we might be entering an era for galaxy cluster size things in which there would be monopole push dominance for nearby non-colliding galaxy clusters. There actually has come out in the last few weeks at least one paper suggesting with hints that this may be happening. So now the last piece of large-scale phenomena is just very simply, people talk about dark energy. I would associate that with the pushes that go with gravitational dipole interaction and possibly gravitational octopole interactions. So now in a paper, we'd be in the discussion section. So here we go. What does this do for general relativity? Well, first of all, general relativity passes a whole bunch of precision tests, and this does nothing regarding that. General relativity solves a whole bunch of problems pretty well that I'm not even trying to touch here. But there is a way to map some of the concepts from my stuff possibly into general relativity. Mass, for example, becomes energy density. Mass current becomes energy flux or momentum, and so forth. And if you do that and believe that that mapping actually makes sense, then in fact you can make a hypothesis that general relativity might not do so well in cases where the isomeric composition changes spatially throughout your problem, or in which the dominant reaches change temporally in the evolution of something that you're studying. And we'll look at that in terms of two very current topics at the moment, which are called tensions between cosmic data and popular modeling. One of the tensions has been around for, I guess, about the last 5 years. It's called the Hubble tension. People have found that they can't explain the Hubble constant for one of the two multi-billion years era if they assume the other assumed Hubble constant for the other era, and they use general relativity and what we know about equations of state. And I would suggest that what's going on here is that for the earlier era, reach one gravitational quadrupole pull dominated and affected the equation of state that people come up with there. That's the equation of state is a pressure density relationship that goes into Einstein's field equations to do what people normally do. For reach two at the beginning, we have dipole push, and the mismatch between reaches might explain the problem. Now, having said all of this, my explanation would go in the right direction, but I can't do anything quantitative with it. There's now some recent analysis of new detailed data that suggests that the Hubble tension may not exist, or may be much less than people have been expecting it to be or have assumed it is. So we just kind of leave this. The same thing happens with the so-called S8 tension and some other lumpiness tensions. These are smaller scale things. But again, the problem, if there is a problem, and there's now some evidence there might not be for some of these, is that popular modeling overestimates how compact stuff should be. And if that estimate is wrong, I would suggest again that dipole repulsion might explain the problem. So now in the rest of a discussion section, one might put in suggestions as to what to do with one's research. In this case, I would suggest that we have a very good way to catalog properties of objects. And for example, there are instances in which n sub 3s is not equal to n sub r. If for charge, for example, each of those is 1, then for charge current, n sub 3s has a new threesome. It's called the velocity of the current. And so n sub 3s is 2. I provide a whole bunch of suggestions for themes for observational work. Let me ask that if you have no idea for a question, ask me to come back to this. For the moment, I will just suggest that obviously a good suggestion for observational work is to explore synergies between my stuff and a lot of ongoing galaxy evolution studies. As far as enhancing popular modeling, same idea, a bunch of ideas here. And I would suggest that it's not news to anybody that it's necessary for cosmology to do something about figuring out how to embrace a combination of dark matter, some of which is self-interacting and some of which is collisionless. So then we would be in the conclusion section of a paper, and I would just be reminding you of what we've done here. So let me just move into the appendix of this paper, and that is to go back and look at gravity and how we get push into gravity. So we would do a very close look, paying some attention to vocabulary, Newtonian type modeling and Newtonian force equations versus Lorentz invariance and Lorentz force equations. We would be very careful to distinguish that one of the objects, we're dealing with the active properties that are manifested in its fields, the other, the two interacting objects, passive properties. This object is just going to interact with the fields. We'd be looking at a frame of reference in detail. And if we do all of this, then here's the very familiar Newtonian gravitational sort of thing. Every term in that equation is familiar. It's appropriate here if you want to do F equals ma, although you don't have to. There's the Coulomb equation that goes with it. What's remarkable here is that the left sides of those two equals force on object P equations does not say anything about velocity of either object or relative velocity to a frame of reference. And so there's an idea that I would propose we could call Newtonian invariance, and it has to do with the masses and the charges that go in here. And we now assume that in modern terms, those are rest quantities. So we go on and ask, what are we trying to do? Object P perceives things about the fields related to object A, and about object A, we're going to use type L modeling, and we're going to assume most of the time the frame of reference is for object P at rest. That makes things a lot simpler. We're going to describe aspects for the fields. We're going to try to keep the two terms that we have from Newtonian type force laws. On the left side, we're going to add more terms that go with new properties. Here is the Lorentz and Maxwell set of equations. They're all familiar to you. What's important here at the moment to remark on is we have a new left side of a force on object P equation. And that's about all we need to know. Just remember things are Lorentz invariant at this point. So we go on and we look now beyond charge into the idea that object A is moving regarding object P, with respect to object P. So we have a charge current. We have non-zero velocity. We have a charge current. We know from Lorentz invariance that we're going to see a larger magnitude of charge, or sense it, or a larger electric field, whatever you want to do. That associates with the charge current. And what happens here is that the non-zero charge current, from the perspective of object P, associates with acceleration in the direction opposite to what it gets from the rest charge in that perception. And the amount of detraction from the original Q sub OA amount is dependent on the charge current, but it is not dependent on the direction of the charge current. So now we're going to do something very similar, and there's not enough of it to change the sign ever. If we go over and look at magnetic moment as a new property, then in fact we can do an example in which our object A has a charge. It has a magnetic moment. We're going to freeze it so that we don't have to deal with that complexity. It doesn't move with respect to object P. We're going to say that the magnetic moment exactly equates to the motion of effects of the motion of sub-objects of object A that have charge. And then we go on and do what we want to do. Magnetic moment effects scale is 1 over r, whereas charge effects scale is 1 over r squared. Charge effects go as 1 over r. The motions mean that we are going to again have object P overestimating the charge of object A. So we have the overestimate associating with the dipole moment. And we get the same sort of thing. There's a dilution. The magnitude of the dilution goes with the magnitude of the magnetic moment, but not with the direction. The dilution subtracts from what we see. And now, if the objects are adequately close together, but not overlapping, we actually get a reversal of the sign of the acceleration. Move this all over into gravity, and you get the chart at the beginning of the chart at the bottom. Basically, object P mass interacting with object A mass pulls object P toward object A. Object P mass interacting with the magnitude of object A internal angular momentum is a push force. And as with our hypothesis about galaxy clusters, the push can dominate the pull, and then you just keep going, you generate the rest of what we've got there. To generalize a little bit, the N3S's, if you add the two up for the two objects, if that's even, you get pull. If it's odd, you get push. There are a whole bunch of aspects that are not addressed here. If you want to ask a question, we'll come back to it. For example, have we described a complete list of properties? The answer is no. And at this point, we would be wrapping up, suggesting the types of physics we started with, the new interpretations that we've given, that we actually may have major contributions here to 90-year-old challenges in cosmology. So I would at this point be thanking you for viewing this presentation. The topic, of course, was some dark matter and gravitational details that explain otherwise seemingly unexplained data. I'd be reminding you that there is a preprint with this. I'd be inviting you to get in touch with me. tjb@alumni.caltech.edu is a good email. And as I said, the observatory that kicked this all off is actually only about 45 kilometers mountainous drive from Caltech. Okay, so now we're into discussion. I hope that some of you have questions. Here's a reminder of things we might want to talk about. If you need prompts, maybe questions, maybe feedback, maybe suggestions, maybe pointers to people who might be interested in this work, what would you like to talk about?